Hey everybody, I'm Alex Debris. I'm excited to talk about DynamoDB with you today. I'm an AWS data hero, work a lot with DynamoDB, and I've talked at reInvent the last 3 years about DynamoDB. I'm excited because this year I have someone that actually knows what they're talking about with me up here. So I'll be talking with Amrith Kumar. Amrith is a senior principal engineer on the DynamoDB team. There are 2 senior principal engineers on the DynamoDB team. It's the highest current engineering position on the team. So lots of deep knowledge that he's going to bring here. We'll do a little bit of infrastructure, a little bit of data modeling, a little bit of everything in this talk to help you learn how to model well with DynamoDB. So to kick it off, Amrith's going to get us going here.
Thanks, Alex. OK, so good afternoon. My name is Amrith. I'm one of the senior principal engineers on the DynamoDB team. Been here for about 2.5 years. The talk is about data modeling, and I'm just going to give you an introduction about DynamoDB and then hand it off to Alex, and he's going to do the rest of it. Let's see if this works. OK. So I'll do the overview. I'll hand it off to Alex to do the data modeling, and then I'll finish with some talk about indexing and transactions. If you were expecting this is going to be an in-depth architecture talk, it is not. There's a couple of links which I've provided. A colleague of mine, Jasso, did a talk a couple of years ago. That's a very good talk. Alex's book, and a couple of months ago, on the 10th year of DynamoDB, we published another paper to follow up on the original Dynamo paper, and I'd strongly recommend all of these if you're interested in architecture. So without further ado, I expect that everyone here knows what I'm going to say. DynamoDB is a key value and document store. It is completely serverless. It is secure, durable, available. And the simple promise we give you is that you can get predictable single-digit millisecond response times at any scale. And I'm going to talk to you about some of how DynamoDB does this. And then you can build applications which can leverage these things. So that's the general idea of the talk. All right. So when we were putting this presentation together, Alex sent me this tweet. And by the way, I strongly recommend the 5-minute video, which is linked there. It talks about how Snapchat built their application. And it talks about how they use Kubernetes and how much data they store. But the thing which really caught my eye when I saw this video was that they scan about 2 billion rows a minute. This is one customer of DynamoDB. 400 terabytes is a fairly large table, not the largest table by any means. But that gives you an idea of the kind of scale to which an application can go. 300 million daily active users, 400 terabyte table, and so on. But scanning 2 billion rows a minute, yeah. So I thought I'd give everyone a little bit of a glimpse at the scale at which DynamoDB operates. So this is a simple thought exercise, OK? You wake up in the morning, you have breakfast. That's the important part of the thought exercise. For every request which DynamoDB does, put 1 sheet of paper on that pile, OK? And work at this till lunch. Can anybody give me an idea how tall this pile is going to be? Shout it out. Empire State Building, OK? Anyone else? To the moon, all right? The answer is yes, it is to the moon. So did we send you the slides for you to review in advance? Yeah, OK, thank you. So in terms of raw numbers, DynamoDB does about 10 trillion requests a day, easily, on most days. Well over that. And each one of those requests is predictably single-digit millisecond latencies. When you build applications which need this kind of guarantee, they don't happen by accident. You literally have to engineer your application to it. Whether it's a relational database or it's a NoSQL database, there's engineering involved. And a big part of that is what Alex is going to talk about, which is data modeling. But in order to data model your application correctly, you need to know something about how DynamoDB works. So let's talk about that. How does DynamoDB scale? Simple answer is 2 things. One, we scale horizontally. And the second is with eventual consistency. If your database requires synchronous writes and you cannot tolerate eventual consistency, your ability to scale will be diminished. If you can only scale vertically, your ability to scale is diminished. But the good news is most applications which need to scale can tolerate both of these. You can scale horizontally, and you can tolerate eventual consistency. In DynamoDB, all of your data is stored in tables. And very much like a traditional relational database, you need to have a primary key for every item. By the way, we don't call them rows, we call them items. So if I use them interchangeably, my apologies. My pedigree is relational databases before I came here. So we store data in items. And being a NoSQL database, there is no strict schema. In this sample data, notice that each item has slightly different structure. But there's one thing which is required. That is the primary key. When you create a table in DynamoDB, we ask you for two things. Well, three. We ask you for a credit card. That's different. You need a table name, and you need a primary key. That's it. And the primary key can either be just a partition key, or it can be a partition key and a sort key. Here I've shown you one with just a partition key. And what we do with that is we store your data sharded on these storage nodes by computing a cryptographic hash on the partition key. Items which fall within a range of hashes go to one storage node. That's easy. We try to keep each partition at about 20 gigabytes. So whether your table happens to have 400 terabytes or more, your partition size is limited. If there's a lot of traffic on your table, we may even have smaller partition sizes. That's one of the ways we give you predictable response time. The thing we do really quickly, 10 trillion times a day, is look at a partition key, figure out which partition it's on, go to the operation, and return to you over and over again, right? So if I were to show you the same data this way, 3 storage nodes and a bunch of rows, DynamoDB is also a regional service. And I said it's durable and highly available. So we replicate all of your data 3 ways. Every partition, there's 3 copies of it. And each copy is in a different availability zone. So if you're requesting your data and your application happens to be in availability zone 1, we will try and serve it from availability zone 1, and so on. But it also means there's 3 copies. If one of them goes away for some reason, we can always reconstruct it. And we'll talk about some of the things which we do to make sure that that actually works. So yes, we have 3 copies of the data. This is how these partitions are laid out. By the way, in case I'm going too fast, somebody just wave or stop me. I did also mention that DynamoDB is completely serverless. When you provision a table, we didn't ask you how many servers you want to provision. We do all that for you. Oops, can't do that. So on these storage nodes, alongside your data, is data for another customer. You may be running an application, and on the same storage node, there may be some of that 400 terabyte snap table. It's our job to make sure that every partition gives the customer predictable single-digit response time. So we move these partitions around on a regular basis. And yes, there's 3 availability zones. There's no guarantee that you will be sharing a storage node with the same partition on a different availability zone. It's completely random. Okay? You make a request to your table. We figure out which partition you're asking for. We get you your data. That's basically what we do. All right. So let's talk a little bit about the architecture. This slide is going to build from left to right. So on the left, you have all of the clients. So your client could be something which is running on a mobile device. It could be another application running in AWS. It could be EC2. It could be Kubernetes. It could be a Lambda, whatever it is. DynamoDB is a regional service. Whether you use the SDK or you directly talk to our RESTful endpoint, the first thing you do is resolve a fully qualified domain name. So if you were in US East 1, region becomes US East 1. If you're in US OS 2, similar. When you resolve that, you will get an endpoint which points to a collection of load balancers. So in this case, I'm showing you that you resolve this FQDN, and you got a load balancer in AZ2. All right. Behind every load balancer is a collection of hosts. We call them request routers. And there's a collection of request routers, which we call a gaggle. Collective is a gaggle. And the job of the request router, which is completely stateless, is, of course, between the load balancers and the request router, we do SSL termination. So your data in flight, let me see if I can get this video pointer to work. There you go. Nope, I guess not. The data in transit is going to be SSL encrypted. It gets to a request router, and the request router's job is three things. First, is the request properly signed by the user? Second, if it is properly signed and it addresses a particular table, does that user have access to the table? And if the user does the user have access to the keys used to encrypt the data for that table? Three things, 10 trillion times a day. Get a request, authenticate, authorize, make sure you have keys. And then, if you do, forward the request to a storage node, which is where the data actually lives. If you're doing a get, send it to the storage node. The storage node stores the data encrypted. So the storage node will decrypt it and send the data all the way back. If your application happens to be in AZ2, we will try and keep this entire thing in AZ2. But remember, we also have the same infrastructure in the other two AZs. So in regions which have 3 AZs, this is what you look like. In regions which have more than 3 AZs, we're in more than 3 AZs. And in the middle of the box there, in the middle of the slide there, there's these other hosts which we manage, which are the infrastructure, metadata. What tables do you have? For each table, where are the partitions for that table? And we cache a bunch of this information. So when you make a request, we look up the partition map, we find out where the data is, and we send it to that storage node. Over and over again. That's what we do. OK. AutoAdmin is a component which is listed in the middle there. I told you we try to keep partitions at about 20 gig. If you insert a bunch of data and your partition starts to grow, AutoAdmin will realize that and will split your partition into 2 partitions and put them in 2 different places, update the partition map. Completely transparent to you. You don't have to do any of that stuff. And we'll talk about transactions later, so I'll skip that one for now. If your requester was in AZ3 and you went to a request router in AZ3, we'll try and serve your request in AZ3, but the request router in AZ3 can talk to a storage node in AZ1 or AZ2. And there are some cases where we actually do that, like writes, or if you do a consistent read, we may have to reach across the boundary. A lot of time thinking about fractions of a millisecond and the time difference between going across AZ boundaries or within an AZ. And we try to make sure that you get predictable response times. So those are the things we do, so you can build on top of that. OK. I did mention that we were completely serverless. So we have 3 AZs worth of capacity, and something happens. Maybe we do a game day, and we take an AZ out. There is enough capacity in the other 2 AZs to serve all of your requests. And we build and we engineer and we test to this on a regular basis, which means, this may be a little bit hard to see, but at the bottom right, there's a little X on the storage node. We are continuously deploying software. If we can take an entire AZ out, we can take a storage router out anytime we want. We can take a request router out anytime we want. And there's no maintenance windows because of this. It's completely serverless, no maintenance windows, and all of this is completely invisible to you as a user. And of course, we do the same thing with load balancers. So customers like Snap or Dropbox or, let's see, Amazon themselves engineer applications knowing how this works. It's important for you to model your data in a way that exploits this architecture. So with that, let me hand it over to Alex. Thank you.
Awesome, thank you, Amrit. And yeah, I love that infrastructure stuff, partly because it's super interesting. So go check out those other resources that Amrit mentioned, especially Jasso's 2018 talk, and the 2022 paper is really cool if you want to get that stuff. But like Amrit was saying, like, this is really useful for you in modeling your DynamoDB applications. So that's what I'm going to talk about here. And if that stuff flew by you, we'll sort of refer to it in different places and reinforce where that helps you in your data modeling, right? So we'll do some data modeling here. I always like to go with some sort of example. I've done e-commerce or social media in the past. We're going to do a game this year, right? So last year, Amazon Studios released New World, which is this multiplayer online RPG game using a lot of AWS services behind the scenes. And Werner got up on stage during his keynote and talked about all the different services, including DynamoDB. One of the things the service is doing is, if you're playing every 30 seconds, it's going to increment your play time just to keep track of how much time you've been playing, right? So they're doing 800,000 writes to Dynamo every 30 seconds, which, as we've seen, is really nothing for Dynamo, but seems pretty big to me. So we're going to be talking about that as the example here. I always like to start off with some terminology. So 4 key terms: table, item, primary key, and attributes. We'll do it in the context of that game. So we'll start off with some users in our game. If you see, we have some users here: Amrit, myself, Janelle, and Chad. 4 records, and they're going to be contained in what's called a table, right? So similar to a table in a relational database, but as we're going to see, different in a lot of ways as well. Now, if you look at an individual record in a table, as Amrit mentioned, that's going to be called an item. So this, Amrit's user record, that's going to be an individual item in your table, similar to a row in a relational database. When you create your DynamoDB table, you have to specify what's called a primary key. And every item you write to your table must include that primary key and must be uniquely identified by that primary key. So on the left-hand side here, we have the primary key for our table. Its username. That's going to uniquely identify every single user in our table, right? We're not going to have 2 users with the same username. It's going to be similar to primary key in a relational database, but different in a lot of ways as well. In addition to that primary key, we also have other attributes you can have here, right? And you can see we have a lot of different attributes, similar to columns in a relational database, with the big difference being you're not going to specify these up front. So DynamoDB is schemaless. There's not going to be a schema that Dynamo is going to enforce for you outside of that primary key. And if you look at these attributes, you can see we have some simple attributes, right? Simple scalar strings, numbers like class, gold, total playtime, guild, things like that. But you can also have complex attributes. You can have lists and sets and maps. We'll talk a little bit about when you'd want to use those. Let's talk a little bit more about the primary key because it's so important to how you work with DynamoDB. There are 2 types of primary key in DynamoDB. So there's, first of all, what's called a simple primary key, which has one element called a partition key. And then there's what's called a composite primary key. That has 2 elements, that partition key and the sort key. And that user table we looked at before, that's an example of the simple primary key, right? It has just that single element, that partition key that's uniquely identifying every record in your table. This is going to be great for simple key value like access patterns. You're only operating on 1 record at a time. But if you have more complex access patterns, then you might want to use a composite primary key. And in addition to users in our application, we're also going to have quests. So let's look at a table with a composite primary key. Here we have some quests that our different users are going on. You can see we're using this composite primary key. It has 2 different elements here, right? We have that partition key of username, but we also have that sort key of guild ID. Now, as you're looking at these records, I just want to point out, if you look at the top 3 records here, those are 3 separate items there, but they all have the same partition key. So you can have multiple records that have the same partition key, and if you're using, this is NoSQL Workbench, this is what I use for modeling a lot. If you have multiple records with the same partition key, it's going to sort of merge that cell together because they're going to be contained near each other on the same partition in most cases. But when you're working with that composite primary key, this is going to be called an item collection. So if I refer to an item collection, that refers to a set of items that have the same partition key. And while you can have records with the same partition key, it's the combination that still must be unique. So you can have records with the same partition key, but the sort keys need to be unique within that combination. If we look at the 2 types of primary key, notice that both of them have a partition key, right? And that partition key is really important. We can go back to what Amrith was talking about. When that request comes in, it hits that load balancer, it hits that request router, right? And that request router is responsible for routing it to the right storage node. It's gonna look up the metadata for your table, it's gonna figure out which item, it's gonna look at the partition key for this item, figure out which storage partition it goes to, and sends it to that storage node. And that partition key is so important because what you're doing is, no matter how big your table is, you're reducing it down to 10 gigs, right? So you can have this infinitely scalable table, 400 terabytes or whatever Snap has, or Amazon Retail, any of that, and you're immediately getting down to 10 gigabytes or less where you can work on something a little bit faster, right? So that primary key, and particularly that partition key, so important to how you do data modeling in Dynamo. So if we look at our users table, right, we have that primary key. That's how we want to access our data, with that primary key. We don't want to do it with those other attributes, which are effectively unindexed at this point, right? They're going to be spread across our table. But that primary key, that partition key, that's how we're segmenting our data. Or if we look at our table with a composite primary key, same deal, right? We want to use that primary key, definitely the partition key, ideally the sort key as well, to access that data, not with those other attributes. So that's the key point with Dynamo, right? With Dynamo, you have to design your tables specifically for your access patterns. And this is going to be different if you're coming from that relational database world where you normalize your data first, you get into third normal form, you set up all your foreign key relations and that stuff, and then you think about how you access your data. You're not going to do that with Dynamo. So I want to talk a little bit about the data modeling process, and then we'll sort of walk through that and understand the features of Dynamo a bit. I always think of it as a three-step process, right? First step is you're sort of understanding your application. You're ideally creating an entity relationship diagram, same thing you're probably doing in a relational database, figuring out which objects you have, figuring out how they relate to each other in your application. Then once you've done that, now it sort of starts to veer off from a relational database, right? Where you actually want to list out your access patterns and think about how you're going to access those different objects and entities in your application. And once you've listed out your access patterns, now you actually do the design work. You go through and you design your primary key specifically to handle those access patterns. And that's where the primary key differs from that relational database. It's not just an auto-incrementing integer that gets assigned to the server. It's going to be something meaningful in your application to help you handle your access patterns. So let's walk through this a bit. We'll start with creating our entity relationship diagram, right? And if you walk through this, your entities are usually boxes. So you have something like users in your application. And as we saw, users have inventory. So you have a one-to-many relationship between users and inventory. Also, users can go on quests. There's a one-to-many relationship between users and quests. And then finally, users can belong to a guild. So users are the subject of a one-to-many relationship as well. One guild has many users. All right, so once we start to know our application, our entities, in that, now let's go and list out our access patterns. And the biggest thing here is you want to be thorough and you want to actually list these out and not think about them just sort of generally in your head, but write them down on a piece of paper somewhere and get specific, right? You want to say create user, increase the gold for user, add inventory to users, all these different things, and list out the different access patterns you're going to have. And note, I like to separate it out into write access patterns, which sort of have different needs. And then also read access patterns, I do the same thing and think about how I'm going to access my data, get a user, fetch inventory for a user, fetch the quest for the users, all those things, right? So I have read access patterns, I have write access patterns as well. And this is going to be a little bit different to you if you have a little trouble thinking about this. Two ways I sort of like to approach it, like if you're exposing a REST API, you can think, what REST API endpoints do I have, right? What use cases do I sort of need to be able to handle in a nice, efficient way? Or if you're building some sort of service, you can say, what methods do I want to expose on my service object that can be used by my application, right? That's a good way to sort of think about that. And the big thing here is to be very thorough, be very specific. If we go look at these different read access patterns, you can look at the two on the bottom. I actually have fetch quests for users, right? I want to get all the quests for a particular user, but I have another one that's really specific, fetch the completed quests for the user, right? That's just a filtered view of that original view. And sometimes you need to be very specific in sort of differentiating between those because there's going to be different access patterns. All right, and then once you've listed out your access patterns, then you want to design your primary key to actually handle those access patterns. And now we can actually, I guess the big thing you want to remember there, you want to be accessing with that primary key, not with those attributes, right? So how do we do this? We can look through our access patterns here. I generally like to start with write access patterns. And if you look at all the write access patterns, right, creating a new user, increasing gold for a user, creating a quest for a user, all of these are single item patterns. We're working on a single item in that request, right? And same thing with our read access patterns. A few of these are what I call single item patterns as well. Get a user, get the quest details for a particular user and quest ID. And remember what we said earlier, that the primary key is going to uniquely identify each record in your table. It's going to be very efficient to go look up an individual item. So working with individual items is a very efficient, consistent, predictable action in your table, right? So DynamoDB has APIs for working with single items. Whenever you need to create, read, manipulate some sort of individual record, that's going to be great there. So getting a user, adding a user to a guild, creating a user, or creating a quest, excuse me. Now, when you're working with single item actions, you have to include the full primary key. So if you're doing put item, get item, update item, delete item, you have to include the full primary key because you want to identify the specific item you're working on. There's not like an update where type clause where you can update all these items that have the same partition key. You have to identify it with the full primary key. And notice that all write actions are single item actions. You can't do sort of like a bulk update write type that. You can do sort of combinations of single item actions and transactions in batch, but all those are just sort of composing together multiple single item actions where you're identifying each item with that full primary key. So that's going to be a big chunk of what you're doing with Dynamo, all those single item actions. But if you look at our access patterns, we also have access patterns where we want to read a set of records in a single request, right? We can handle those with Dynamo. First one we can handle, if you look at this top one, right? I want to get all the inventory for a user. And if you look at our users table, remember we just embedded the inventory on our user item, right? So we have this list that contains all the inventory that this particular user is getting. So if we want to get the inventory for a user, we're just doing that single item action, that get item, to read that user record, right? So you can do that in certain scenarios, but more commonly you'll probably use a different pattern. So let's look at a different one, fetching quests for a particular user, right? And we can go back to our table. Our quest table has that composite primary key. Remember that we said that all the records with the same partition key are in the same item collection, right? And you can use what's called the query operation. And in the query operation, you can retrieve multiple records that have the same partition key. Remember what that partition key is doing for us. It's narrowing our table down from infinite size down to 10 gigabytes, right? So it's narrowing where we're going very quickly. We can retrieve these items together. So we're pre-grouping them together in some particular way, right? And query is helping us actually access those. Now within this item collection, they're going to be ordered according to that sort key. And we can use that in smart ways of how we want to order these records to be returned to us or how we want to filter them in that query. In this particular one, I'm using what's called a UL ID. So it's kind of like a unique ID that has a timestamp prefix encoded in it, right? So we get time sortable IDs. So the first 10 characters you get here, if you look, that actually corresponds to that quest started at date, right? So now I'm getting some uniqueness of that UUID, but I also get that time sortability that helps me using that sort key. And I can use that sort key to actually filter my data, right? So I can query within an individual partition, but let's say I want to narrow that range to a particular time range. I can add conditions on that sort key and say, hey, when the quest ID is between this time and this time, which is January 1st and August 1st, right? And it'll narrow down, and it's just going to get those records that match that for me, right? So that query API is going to be really powerful for you. Again, that's what you're doing is reading a set of records, right? Getting all the quests for a user, fetching all the members for a guild. When you're using that query API, you have to include the partition key, but you can also include those sort key conditions. And that can help you do things like filtering on a time range, getting you the most recent, alphabetical, things like that. I talked a little bit about like 2 patterns to handle related data, right? We have the embedded pattern where inventory is embedded on that user. We also have this item collection pattern where quests have the same partition key. Like, when should you use each one? The embedded pattern is good when you have like a smaller and bounded set of relations. I'm not going to have a user that has 1,000 inventory items, right? They're going to have a weapon, a shield, some boots, a jacket, something like that, right? So a pretty small amount of them, it keeps my items small. I'm not going to run into item size limits or be paying a lot for those. Also, I'm not searching by those relations directly. I'm not saying, which user is wearing this cloak or something like that. I'm saying get that user, and I want to render out all the inventory that they're wearing. So you can use that embedded pattern there, but probably more often you'll use that item collection pattern using that query API. And that's good when you have a large and unbounded set of relations, right? I don't want to limit the number of quests someone could go on just because of the DynamoDB item size or the number of e-commerce orders someone can make. Also, I might want to fetch that related item directly, and if it's a separate record, I can index that in different ways that are helpful there. Last thing I want to look at with these read access patterns, notice we have a pattern of fetch users by guild, right? So we want to retrieve all the users that belong to a certain guild. But if we look at our users table, right, it's already partitioned according to username because we have this get user by username access pattern that's getting it. But then our guild is some other attribute. We said that it's not efficiently indexed for that. So how do we handle multiple access patterns on the same piece of data? And that's where something called secondary indexes come in. Right? And these are actually fairly similar to indexes in your relational database with a few differences. But basically what's happening here is data from your main table is getting copied onto separate partitions with a new primary key. So you can declare this on your table, basically give you a new primary key, and it's going to copy it onto separate infrastructure. So if we look at our table here, and we want to be able to access these the users by their guild, right? We can declare a secondary index where we set up the guild value as the partition key, where we set up the username as that sort key, and now what we have is a secondary index. This is the exact same data, but it's just shifted in a different way where our primary key uses that guild and username, right? And then we can query that efficiently. So again, with secondary indexes, data from your table is copied on separate partitions with a new primary key. I say new primary key, but that's a little bit with an asterisk. It's not a true primary key. It's not maintaining uniqueness and things like that. But in terms of the query API, it acts very similar to a primary key in your DynamoDB table. You can use simple, you can use composite, things like that. Now, the great secondary indexes, you can only use them for read-based operations. So you can enable additional read patterns, but you can't do writes to your secondary index. All your writes need to flow through your main table, and they'll get replicated out to those secondary indexes. And again, the key point here is this is going to help you if you have multiple access patterns on the same item. They can also provide filtering using a pattern called sparse index. So let's go back to those patterns I talked about earlier. We want to fetch the quest for a user and also fetch the completed quest for a user, right? How can we efficiently filter that out? We show how you can get all the quests for a user, right? You go to that item collection, use that query, specify that partition key, but we basically want to filter out all the records that don't have a quest completed at date, right? And we could just fetch all those and filter it in memory, but ideally we could have a more narrow, more focused query. So what we can do here is set up a secondary index where we set up the partition key, or the username as the partition key, the quest completed as the sort key, and that's going to filter those out for us. And now we have this secondary index that's already provided the filter, filtered out the uncompleted quests, and now we can get exactly the quests that we need here. So just a couple takeaways from the basic data modeling portion, and I'll go into some more advanced sections, right? Key part here is you want to understand your access patterns and model explicitly for them, and that's where it's going to be different from a relational database. Rely heavily on those primary keys, but then you can use those secondary indexes for accessing your data, reading your data in different ways. We talked about relationships and the different patterns you can do there, when to do embedded, when to do that item collection query pattern. And then we talked about different ways with filtering, right? You can filter with that partition key. We filtered all the quests down to get just the quest for a particular user using that partition key. And then we wanted to filter it even more with that sort key, right? So we said all the quests for this particular user within this particular time range. Then we could filter it even more using that sparse index pattern where we said, hey, only include these items if they have that quest completed at value, so we filter out the uncompleted quests, right? And I think one thing you want to take away with Dynamo is you want to limit the number of requests you're making to Dynamo. Ideally, all these access patterns you're doing, you can handle with a single request to Dynamo, which is going to give you that consistent response time, that consistent predictable response time that Amrit mentioned. Also, you want to limit discarded data. You don't want to read a bunch of data from Dynamo and discard it in your application. What you want to do is lean on that primary key and those secondary indexes to do the filtering for you. So ideally, you've got exactly the set you need from your response. All right, let's move into single table design, because I know people love a little bit of single table design. So if you're new, when you're new to Dynamo, you might hear this pattern called single table design. I want to talk through that. First of all, what it is, kind of how it works, and then why you might use it, right? What are the benefits of using single table design? And really my favorite is like what single table design teaches you as you sort of learn that pattern. So let's start off with what is single table design. It's basically when you're putting multiple heterogeneous entities into a single DynamoDB table. If you look at the DynamoDB documentation, it's going to talk about how NoSQL design is different, and it'll say you should maintain as few tables as possible in a DynamoDB application, right? So if we go back to our ERD, right, we have these 4 different tables, and it's saying rather than having a table for each like you would in your relational database, ideally you have fewer, maybe just one table. And it doesn't mean by cutting out entities, but actually combining them into the same table. And you might think, hey, we already did this, right? If you remember users in inventory, Let's go back to our users table, right? And we had our users, but we also just embedded that inventory in our users. So is this single table design? I'd say not really. In addition to putting multiple different entities in a single table, I think single table design is you're also using generic primary key names, right? Rather than having sort of these specific names like username, like quest ID for your primary key, you have more generic names. So I want to walk through how we'd combine our users table and our quest table into a single DynamoDB table. Let's start off with some users. So I have myself and Amrith here in our table, those two user records. A couple things to call out, notice that we're using generic names for our primary key elements, right? We don't have username, we don't have quest ID, we have PK for partition key and SK for short key. So that's that single table design, those generic names there. And if you look at the values for our primary key, notice that they're a little funkier, right? We might be combining multiple different values in there. We might be prepending it with the item type in there to help signify what kind of item we're working with there. All right, so let's add a few quests in there so you can see in our table now we have 5 records. We still have our 2 user records, Amrith and I, but then outlined in red now you can see we've also added a few quest records in here. A couple other things I want to call out here. Notice that the primary key values are going to be different for a sort key ID. The patterns are going to be different there for a quest than it would be for a user. Also notice that I have this type attribute that I'm including on every single item in my table, because now when I'm reading records back from my table, it's easier for me to determine what type of item I'm getting and deserializing it into some object in my application. Finally, if you look at the attributes here, right, notice that they have different attributes, right? Users have user-like attributes, quests have quest-like attributes. Because DynamoDB is schemaless, I didn't have to declare these up front. They'll just sort of handle all that for me. So that's the basics of single table design, right? We're putting lots of different items in a single table. We're using these generic primary key names. Let's talk about why you would do this, because this is very weird if you're sort of new to this, right? So I think the first reason is this can improve performance by making fewer requests, which I said is one of the points of DynamoDB. Ideally, you're handling each use case with a single request. Let's see how that could happen, right? If we look at our table here, notice we have an item collection. We have a set of records that have the same partition key. But if you look, even within that item collection, right, we have different types of entities in that item collection. We have our user record. We also have a couple of quest records that belong to that user. And that can help us. Maybe we have an access pattern that says list all the quests for a user, but we also want to get that user record with it to sort of enrich those quests, right? Just like you would with a join in a relational database. And that's basically what we're doing. We're pre-joining our data. We're at write time rather than at read time. And now it's a consistent operation at read time. Also, we don't have to perform that sort of that join, that CPU work every time we do a read, right? We do it once at write, and it's good to go. So that can reduce the number of requests to Dynamo, because we're not going out and getting a user and going out to getting a request, so we can do it with one query to get all those in one request. Second benefit here is that it can reduce cost. And to understand that, we need to understand sort of how DynamoDB billing works. So DynamoDB billing is different than more serverful billing because you're paying for reads and writes directly. You're paying for the amount of data you read and write from your database rather than paying for server resources, right? So a traditional database is going to charge you on CPU, on RAM, on IOPS, all that stuff, whereas Dynamo is going to charge you on what are called read capacity units, RCUs, and write capacity units, WCUs. And read capacity units allow you to read 4 kilobytes of data from Dynamo. Write capacity units allow you to write 1 kilobyte of data. And that's what you're actually charged on with Dynamo. So there's a tighter link there between what you're actually doing and how you're charged for it. Another thing to note here is writes are charged for both your main table and your secondary indexes. So if you have 3 secondary indexes on a table, you write a new record in, you're going to get charged on that, your main table, but also for all 3 of your secondary indexes if it's replicated out to that. So how could this actually be cheaper if we're doing single table design? Let's go back to our user record and just think about it and how this works, right? We have this user record, and notice that it's kind of a split record, right? If you look at some of those attributes, we have a lot of smaller but fast-moving attributes, right? Like gold. Every time I'm picking up gold in the game, I have to go increment that gold value for my player. Like we're saying with total playtime, every 30 seconds you need to increment that total playtime to update that total playtime for that user. In addition, we have one attribute, this inventory attribute, that's a larger but slower moving attribute. It's larger because it has lots of different items in there, or different inventory instances in there, but it's also slow moving. You're probably not changing your inventory a lot. So when you think about DynamoDB billing, one thing I always tell people is do the math. Since you're actually charged on the resources you're consuming, you can actually do the math on this stuff, get a decent estimation of how much this will cost you, or even looking at 2 different ways of designing your table and see which one will be cheaper. So let's do the math here, right? Here's our situation. We have a 4 kilobyte user item, which is basically broken into less than a kilobyte of core data and about 3 kilobytes of inventory. Maybe we have 3 secondary indexes on our table, and we want to increment that total play time every 30 seconds. To do this, as we've sort of structured out, if someone plays an hour on our game, it's going to cost about 2,000 write capacity units to do that. In the math here, 4 write capacity units because it's a 4 kilobyte item, 4 different targets, our main table, 3 secondary indexes, and it's going to happen 120 times an hour because we're doing it every 30 seconds. And if you look at that, the 2 big culprits here are we have this 3 kilobyte inventory item that's not changing, but we have to rewrite it every time we go increment our total play time. And it's also getting replicated to 3 secondary indexes when those secondary indexes probably don't need to know about the inventory for the user, right? We only need the inventory for the user when we're fetching the user to sort of load up the game or something like that. So what we could do is use more of a single table design model and do vertical partitioning. And there's a great blog post that just went out on the AWS blog about how to do vertical partitioning in DynamoDB. But this is the idea here where you might chop up an item into multiple pieces here, right? And we have our small, fast-moving user item that has the gold, it has the total play time. That's going to get updated a lot, but it's a small item. It's less than a kilobyte, right? We also have a separate item that contains our inventory. That's our larger, slow-moving item. Not going to be changing as much, but it's a lot bigger, right? And let's fix the math here on how we do it. First of all, instead of having a 4 kilobyte user item that we need to update, whenever we update the total play time, we only need to update that smaller one, right? So now it's a kilobyte or less. And now we can change our math, and 1 hour of playtime is going to be less than 500 write capacity units, right? So a fourth of what it was before. And you might say, I'm cheating. Why didn't you just put these in 2 separate tables? But one thing it allows us to do by being in the same table is we can still have that query pattern where if we need to fetch the user and that user's inventory, that's still just one operation. That's a query operation. And we'll get sort of the user metadata and we'll get the inventory all in one request. And the query cost is not going to change there because query is based on the total amount of data you're reading, not how many items you're reading. So this is still great for us. So that's the second benefit of single table design. It can reduce the cost. Third benefit is it can be a lower maintenance burden, right? You might be coming from a relational database and think, hey, I can have 50 tables in my relational database. It's just one server instance I need to manage. But each different DynamoDB table you have is going to be a different piece of infrastructure that you need to set up alarms for, you need to set up capacity for, all that sort of stuff. So if you put it all in one table, or fewer tables at least, now you have less auto-scaling to worry about, fewer alarms, all that stuff. And really, my bonus, the reason I like single table design the most is it forces you to think about DynamoDB differently, right? It helps you to realize that even though the word table is the same coming from a relational database, it's not like modeling a relational database, right? It makes you think about your access patterns first, not denormalization. Because if you hear, hey, we should be using a single table for this, you're not going to be normalizing your data into a table for each entity, right? And because of that, you start reaching out and thinking about how to reduce multiple requests. You start thinking about latency and how that interacts. Then you start thinking about cost. You think about the shape of the data and see how can I optimize that to work better, right? So my big takeaway on single table design is like, I like it. I think your pattern should be able to work with single table design, but you don't have to feel boxed in, right? Make sure you're learning the mechanics, learning the theory, because I think that's going to teach you DynamoDB's data modeling a lot better. And then understand where you can relax this and maybe have a couple different tables if you have different needs across items in your table or things like that. All right, so that's single table design. One other topic I want to talk about that I think is not well understood or is underrated about DynamoDB is just around how DynamoDB's consistency, how they handle constraints and transactions across your application. I think if you're coming from a relational database, you hear eventual consistency, that seems scary. Or maybe you've worked with other NoSQL databases and you worry about how you can maintain conditions and constraints in your data. And I think DynamoDB is kind of unique in that way. So let's go back to what Amrith was talking about earlier, where remember, your table is going to be sharded into these multiple different partitions. So we have 3 different partitions, each one holding a different segment of our data. But within one individual partition, we also have 3 replicas, right? And that's where the issues of sort of data consistency come in, right? When you have replication, now you have to think about consistency across those. So let's look at that a little more closely, right? Within a particular partition, we have these 3 nodes. They're syncing data across each other. This is going to be called a replica group. And now if I make a read to DynamoDB, someone wants to go get Amrith's user record, that's going to go through the request router, right? That's where it's going to find out which partition it needs to go query, and it's going to get 3 nodes back, and then it's going to send it to one of those 3 nodes, and it can be any of those 3 nodes that can actually answer that request, and it can maybe even be kept in the same AZ as Amrith was mentioning earlier. But a write operation is different, right? If I want to do a write operation and update that Amrith user record, it's not going to work the same way. It's not going to go to any of those nodes, but one of those nodes is going to be elected the leader. So within a replica group, there's always a leader. It's a single leader. This is different from how the original Dynamo worked in the Dynamo paper from 2006. This is different from how Cassandra works in other NoSQL databases, but there's a single leader in a Dynamo replica group. And now when you do a write, that request router is going to send it to that leader node. That leader node is going to write it locally. It's going to reach out to the 2 replicas and tell them to write it locally. And as soon as one of those replicas comes back with a response, then it's going to return to that user and say, hey, this has been durably committed to your DynamoDB table. But you can see there's that 3rd node that maybe hasn't quite committed that read yet. And you can imagine if someone comes in at that particular time and requests that Amrith record, maybe they hit that 3rd node that's just slightly behind, and that's where you can get an eventually consistent read. That could be a stale read that's slightly out of date with what's been acknowledged in your application, right? So Dynamo does have that. Again, just to cover what's going on here, each partition is going to replicate it across 3 nodes, across 3 AZs. This is called a replica group. Any node can serve a read by default, but the leader has to process that write. And when that leader's processing that's right, it's going to make sure that 2 of the 3 nodes have written it, so at least one of those replicas as well. So why use a strong leader, right? This is different from Cassandra. Why use a strong leader? And I think there are 2 big benefits of a strong leader that are underrated. Number 1 is if you do need strong consistency on reads, you can avoid it in DynamoDB by going straight to the leader, right? So we saw how you can get a stale read from that sort of lagging node, but that's unacceptable to you. When you're doing a read request, you can specify, I want a consistent read on this one. And now when it goes to that request router, it's going to route it to your leader node, which has the most recent, the most up-to-date version of that data, and you'll get the latest version. You won't have any eventual consistency issues there. So that's one benefit. That's nice. But I think the bigger benefit is on the write operations, right? There's one canonical version of each item. So with Cassandra, you could be writing to multiple different nodes at the same time in a replica group, and they could both accept those writes. And now you need to figure out how to reconcile those. Is your database going to reconcile it using something like last write wins, or do you have to push that down to your application layer, right? There's just difficult reconciliation logic that you need to think about now. Also, not only that, but it's difficult in a lot of these NoSQL databases to handle conditional writes, right? Because there could be multiple versions of that data, you need to do coordination at write time. So, and coordination is expensive, so you have to reach out to all those nodes to coordinate to agree on a value. Whereas with Dynamo, with that single leader, you can do cheap and easy conditional writes, right? And conditional writes are super beneficial. I always say when you're doing write access patterns, make sure you have a column that says conditions, because there are certainly conditions that you want to maintain in your access patterns, right? You don't want to have multiple users with the same username, right? You don't want to add a user to a guild if they're already in a different guild or something like that. So condition accession is super useful, right? You can assert the existence of an item. So if someone's selling a piece of inventory, you can assert that they actually have that piece of inventory, so they're not selling something that doesn't exist. Or you can assert uniqueness, right? Non-existence, right? When we're creating that new user, we want to make sure there's not a user with that username already. Or you can assert constraints based on attributes in the items, right? Lyft uses DynamoDB to schedule ride sharing, right? And when I'm in an application, I request a Lyft ride. In the backend, it can go read from its DynamoDB table and say, hey, give me all the drivers that are currently signed in, that don't have a rider, that are in this particular area. And that could be an eventually consistent read. Maybe that's a little behind and 2 of those drivers actually have rides. But when that backend actually goes to assign it to me, it can assert conditions like saying, make sure this driver is still on and active, make sure they haven't already picked up another ride, and you can prevent yourself from getting into a bad situation there. So make sure you're using these conditions. And the great thing about this is there's no latency penalty of doing this because of that single leader, right? There's that one canonical version of that record. That write's going to go to that single leader. It's actually going to be faster if your conditional write fails, because now it doesn't need to reach out to those other replicas in your replica group. Another great thing about this is because conditions are easy, we can also add in transactions, right? So DynamoDB has transactions. These were added in 2018. This allows you to operate on multiple items in a single all or nothing operation, right? So if two users are trading in your game, one's selling a weapon, one's buying it, you can assert that, hey, this user actually has the weapon, this user has the amount of gold to make it happen, and use a transaction that way, right? So you get all those benefits, which are more difficult if conditions are expensive in your database. You can also use this for idempotency, right? If you have, maybe you're incrementing some sort of counter through stream processing, you can include a client request token through transactions to make sure that that request is idempotent. Big thing here with transactions, as with any transactions, like watch out for contention, right? You don't want to be involving a record in transactions if it's a very hot item, because then there's going to be contention in it. This is true in a relational database, in NoSQL, any of that stuff. So just the takeaways here, because again, I think this is really underrated about how Dynamo works with consistency, right? Use those condition expressions as much as you can. They'll help maintain those constraints in your data. You don't have to worry about that as much. Again, there's no additional cost. There's no additional write cost. There's no additional latency hit. It's actually faster if your condition expression fails. And you can use that to maintain uniqueness, prevent double assignment. If you need to, that's where you can pull in DynamoDB transactions if you need to maintain constraints across multiple items. Big issue there, watch for contention, and there's also going to be an additional cost for that transaction management. And in fact, I think these things are, on the right path about consistency, that's the important part. But if you do need strong consistency on your reads, that's where you can use that consistent read if it's truly needed, give you a strongly consistent view of your data, with a note that this isn't available on global secondary indexes. All right, now on some of that stuff, Amrit's going to talk about some of the infrastructure underlying that.
Thank you, Alex.
Yep.
Let me see if I can get my microphone.
Yeah, sorry.
All right. So how do indexes work? Alex talked about how indexes are stored as separate tables. Let's take some sample data here. I have orders, customers, and date, and potentially other attributes, which I'm not showing you here. The thing I'll point out is the second, third, and fourth rows are with the same customer. That's customer ID, which starts with 204. And all the order IDs are unique. So on this table, the order ID is probably the primary key. It's unique. That's the access pattern. Give me everything about a particular order. Very common thing you'd want to do. Another thing I would want to do is give me all the orders by a particular customer and give them back to me ordered by the date on which the order happened. So I could have an alternate access pattern with the customer ID and the order date. And the way in which you do that in DynamoDB is you have the table, and the table is defined with the partition key being the order ID, and the global secondary index is defined with the customer ID and the order date. Alex did point this out. I'm going to stress the primary key on a table has to be unique. There is no primary key on an index. There's a key. There could be non-unique attributes, but there's no guarantee that it's going to be unique. Keep that in mind. So there's the table, and there's the GSI. You can query the table all day long without impacting the GSI. You can query the GSI all day long and not impact the table. That is something which you cannot do in most other databases. It's a useful pattern to keep in mind. So how does an update to a GSI actually happen? Let's assume I need to write another order here. A customer, in this particular case, 424 ordered something else, or sorry, the customer ID is 156 something or the other, ordered something new. The item is written first to the table. Asynchronously, the item is propagated to the GSI. I mentioned two ways in which DynamoDB achieves scale. One is horizontal scalability, and the other is eventual consistency. Alex talked about eventual consistency on the table. This is eventual consistency on the index. By not requiring the GSI to be updated synchronously, we give you predictable single-digit millisecond response times. But your application needs to understand that if you write an item to a table and virtually instantaneously you query the GSI, maybe you're not going to see the item there. Propagation delays sub-millisecond, sometimes in the low milliseconds. You'll get the item into the GSI. Keep that in mind. OK. The other thing which Alex talked about was transactions, the way in which we do transactions in DynamoDB. For those of you who are familiar with transactional and relational database, very, very similar. In the middle column there, with the fleets of hosts which we operate, I mentioned one called a transaction coordinator. For those of you who are familiar with two-phase commit, it's the same thing. So the way in which two-phase commit works is, and we get standard ACID semantics as a result, the way in which it works is that every request to do a write to multiple items starts with a begin. The transaction coordinator comes along, says, you're beginning a transaction. There's a bunch of writes. I'm going to send the writes to the various storage nodes. Now remember, these writes could be to multiple items. For each item, you know in the write what is the partition key being modified, identify the storage node, send it to that storage node. Could be in different tables. Once the writes are done, there's a prepare. The transaction coordinator tells all the storage nodes, prepare. At this point, all the condition checks are evaluated, and the storage nodes decide whether or not they're willing to accept the write. One of two things can happen. All the storage nodes can come back and say, we're good. OK. If that's the case, the transaction coordinator says commit, and all the writes happen. Guaranteed. Either all of them happen, or suppose the other thing happens. At least one storage node comes back and says, I'm sorry, condition check failed. The transaction coordinator comes along and tells all the storage nodes, roll back. Either all the writes go through, or none of the writes go through. We give you transactions here. Again, if you're doing the kind of thing which Alex was talking about, you're handing some gold from one to another in exchange for some weapon, or the rideshare example, using a condition check in the transaction will make sure that if the condition check fails, the transaction rolls back. OK? Very useful pattern. The thing which I love the most about all of these things is listening to people who use DynamoDB and figuring out how they do it. So I understand NoSQL data modeling is different from the standard relational database, but many of the things which you do with a relational database carry forward. Take the time to learn the proper DynamoDB concepts and model your data appropriately. Think about what it's going to cost. Think about what the latency is going to be. Think about what the underlying infrastructure is. Think about the API design which you want. And finally, when you're operating your application, think about what it's going to take to do that. How many tables do you need? Fewer tables is easier for you. So with that, I'm going to come on up, and we have, I think, a couple of minutes for questions, but we're going to be outside if anybody wants to stop us afterwards. I'm going to be at the database booth, so if you want to come by there as well. There's a microphone here somewhere in case people want to
we'll probably have to take it outside. We asked for 4 hours. They gave us one, so we used the whole hour. But we'll be outside as long as you all want.
All right. Thank you.